Our first topic of the week is on equilibrium at a point, also known as particle equilibrium. The point of equilibrium is essentially the point at which multiple forces meet. On this slide and the next, there are real-life examples demonstrating equilibrium at a point. Pause the video here to analyze these images and try to identify the points of equilibrium. On these first two images, there are multiple points of equilibrium, but I'll just highlight a few of them as an example. These red arrows are just the forces that will act on the highlighted points. Again, pause here to take some time in identifying the points of equilibrium. The two pictures on the left both have one point of equilibrium where various parts of the system join together. The picture on the right is of a biological cell, and there are multiple points of equilibrium like the ones I'm marking. Once again, these red arrows are the forces exerted on each point of equilibrium that I highlighted. Consider a particle identified by point P that is subjected to several forces as shown to the right. Try to answer the following questions on your own before the answer is revealed. What motions can the particle undergo, and why do we not consider rotation? To answer the first question, the particle can translate in both the x and y directions on a 2D plane. As for the second question, the moment arms are vanishingly small, meaning that the force exerted by these moments is negligible. Let's look into how we construct FBDs for a particle. As always, we start by establishing a suitable coordinate system. We'll pick right and up as our positive x and y directions respectively, and although we don't consider moments in these types of problems, we should still select a moment coordinate system to get in the habit of doing it. So counterclockwise will be our positive moment direction. Next, we have to determine which part of the body that we're studying and draw it out. Really, the only body here is the particle, so I'll redraw the particle and all the forces acting on it as we're told in step 3. In step 4, we write and solve the governing equations of equilibrium, which are the sum of forces in the vertical direction and sum of forces in the horizontal direction. Since all forces are acting at an angle, we must break them up into their corresponding x and y components. The sum of Fx equals 0 accounts for all the x components of each force. Our equation is then 0 equals ax plus bx minus cx minus dx. The sum of Fy equals 0 accounts for all the y components of each force. Our equation is then 0 equals negative ay plus by minus cy plus dy. Note that the equation m about p equals 0 does not tell us anything since the moment arms are negligibly small. In other words, there are no points within a point to create a moment. Finally, we interpret our results. We conclude that the particle will be in equilibrium when the force components in both the x and y directions are balanced. Alternatively, the particle will be in balance when the vector sum of forces is 0. In our first example, we'll analyze 3 forces at a point. Suppose that the spring scale angled 30 degrees from the horizontal exerts a force of 5 kilogram force, which is the same as 49.1 newtons. What are the forces acting in the other 2 springs? Feel free to pause the video here to try this problem out for yourself. To begin, we establish a suitable coordinate system. Again, up and right are going to be our positive direction, and to make it a habit, we'll set counterclockwise as our positive moment. Next, we determine the part of the body that we're studying, which is just the ring, and so I'll draw out the ring. Step 3 asks us to draw the forces acting on the body, so I'll add these to our diagram. Notice that the problem is now simplified to forces at a point. The next step is to write and solve our 2 governing equations. Before we do this, let's break up the 5 kilogram force into its corresponding x and y components, which are 5 times cosine of 30 degrees and 5 times sine of 30 degrees respectively. The sum of Fx equals 0 accounts for all forces acting in the x direction. Our equation is then 0 equals negative F1 plus 5 times cosine of 30 degrees. This gives us a solution of 4.33 kilogram force for F1. The sum of Fy equals 0 accounts for all forces acting in the y direction. Our equation is then 0 equals negative F2 plus 5 times sine of 30 degrees. This gives us a solution of 2.50 kilogram force for F2. Again, we're neglecting moments, so we can move directly to the final step, where we sketch and interpret the results. I'm currently redrawing all forces acting on the ring. We can also verify that our solution is correct by drawing a force triangle. If the addition of the 3 force vectors from tip to tail forms a closed shape, then we have satisfied the equilibrium equations. The second and last example for this lesson is of a suspended box. Find the tensions on the 2 cables attached to the corners of the box. Feel free to pause the video here to try this problem for yourself. Like before, we begin by establishing a suitable coordinate system. Up, right, and counterclockwise will all be in the positive direction. Then we determine which part of the body is to be studied and draw it out. In this case, it's the junction where the 3 cables meet, Q. Now we draw the forces acting on the body. This includes the 3,000 Newton force and the 2 cables, which I will call T1 and T2. The next step is to write and solve our 2 governing equations. Before we do this, let's break up the cable forces into their corresponding x and y components. The x and y components of T1 are T1 times cosine of 45 degrees and T1 times sine of 45 degrees, respectively. And the x and y components of T2 are T2 times cosine of 30 degrees and T2 times sine of 30 degrees, respectively. If we try to write out the 2 equilibrium equations, we will notice that both equations include 2 unknowns, which are T1 and T2 broken into the component forces. To solve for the tensions with 2 unknowns, we must isolate one of them, either T1 or T2, and substitute it back into our equation. For this solution, I will isolate for T1 using the sum of Fx. The sum of Fx equals 0 accounts for all forces acting in the x direction. Our equation is then 0 equals negative T1 times cosine of 45 degrees plus T2 times cosine of 30 degrees. Isolating for T1, we get T1 equals 1.22 times T2, which is our first equation. The second equation is the sum of Fy equals 0, which accounts for all forces acting in the y direction. Our equation is then 0 equals 3,000 newtons minus T1 times sine of 45 degrees minus T2 times sine of 30 degrees. Now we can substitute equation 1 into equation 2 to solve for T2. Once we perform all the intermediate calculations, we get a force of 2,210 newtons for T2. Finally, to solve for T1, we plug our value for T2 of 2,210 newtons back into equation 1, which gives us a force of 2,690 newtons. Again, we're neglecting moments, so we can move directly to the final step where we sketch and interpret the results. I'm currently redrawing all the cable tensions. Once again, we can verify our results by constructing a force triangle. To summarize the content of this lesson, there are a few blanks on this slide that I'd like you to try filling out on your own before seeing the answers. In particle equilibrium, the point at which multiple forces meet describes the point of equilibrium. Generally, this point is also the body of study when it comes to drawing FBDs. Only forces in the x and y directions are considered, and the reason for this is explained in the next point. So the reason for this is because we neglect moment calculations since rotational forces are vanishingly small. Remember that there does not exist a point within a point about which you can take a moment. Essentially, what this means is that a point is too small for any moments to act upon it. And finally, when three forces are acting at a point, we can use a force triangle to verify our answers. Each force must be added from tip to tail and make a closed shape.